we continue to look at line integrals, but before doing that, just a reminder about dot product. Yeah, that if you have two vectors, let's say they're called v and how about w, and there's this angle between them, please recall that cosine of that angle is equal to the dot product over the magnitude of the first vector times the magnitude of the second vector. Now, all the things in the denominator have to be bigger than 0, right? So, so you don't want to use this formula when you have a vector of 0 magnitude, because then you end up dividing by 0. But magnitudes can't be negative, they're lengths. Yeah, so bigger than 0. It means that the sign of the dot product, so the sign of the dot product, if v dot dot w is greater than 0, something happens, right? So think about, cosine of what kind of angles give you a positive number, right? So then theta is acute. If v dotted with w is less than 0, then theta is obtuse. So, for instance, right there, because that angle is small, without even knowing much about the vectors v and w, just based on how they're drawn, we can say that the dot product is a positive number. And that's going to come up a little later in the material for the day. The idea is going to really be like one vector is fixed. Okay, so maybe this is the fixed vector. And then another vector is going to come along. Maybe I'll draw that other vector. We don't know. Okay, maybe the vector's there. Or is it there? Or is it there? Or is it there? And we're going to talk a little bit about what kind of vector you would want compared to the fixed vector to get the dot product to be positive versus negative versus 0. Okay, so of course, like these ones, either these two vectors dotted with the fixed vector would give you a positive number, while these two vectors here, pictorially dotted with the fixed vector, would either these two vectors there dotted with the fixed vector would give you a negative number for the value of the dot product. Okay, to help review some stuff from last time though, let's just ask and answer a question. If C is the following, okay, so in the xy plane, we've got this curve. There's 2, here's -1, and then here's -4, and we have this part of a circle. Okay, and so this is part of a circle of radius 3. It's just been shifted down 1 unit. And f of x comma y is equal to x cubed y to the 4th. Let's find, or at least set up integrals. Let's just set up integral over c of f of x comma y ds, and we'll set up also integral over c of f of x comma y dx, and integral over c of f of x comma y dy. Now, let's go ahead and parameterize the circle here. So, in starting our answer, we've got the circle C that's drawn should be x of t is equal to 3 cosine of t, y of t is equal to 3 sine of t with a -1, and let's see, based on second and third quadrant, we should have pi over 2 less than or equal to t less than or equal to 3 pi over 2. All right, so then we'll just set up the integral, right? So we're not gonna work through all the details here, but we should have the integral over c of f of x comma y ds should be integral t values from pi over 2 to 3 pi over 2. We should now write down x cubed y to the 4th, but we need to plug in 3 cosine of t, and we need to plug in 3 sine of t minus 1. So we'll have 3 cosine of t to the 3rd, and 3 sine of t minus 1, that replaces y, okay, raised to the 4th. And then the ds, well, that's going to be root, and then we should take the derivative of 3 cosine of t, so how about -3 sine of t, and then square that, square the value of the derivative. plus, and then we need to differentiate 3 sine of t. Well, that'll be 3 cosine of t, and we should take that and square it dt. Now, if we set up the integral of same function with respect to the coordinate axes, so with respect to x dx, we'll have most of this is the same. Integral from pi over 2 to 3 pi over 2. We have still here a 3 cosine of t quantity cubed and a 3 sine of t minus 1 quantity to the fourth. But because we're talking dx, we only take dx dt, which is negative 3 sine of t. And we have then times dt. Now the integral over c of f of x comma y dy will be integral pi over 2 to 3 pi over 2 of 3 cosine of t quantity cubed times 3 sine of t minus 1 quantity to the fourth. And then we need dy dt, so we'll have here 3 cosine of t dt. And that should finish this question. Let's do another one. So how about let's just set up the line integral of f of x comma y equals, let's write that a little cleaner, equals y over x, and we'll do this over the following curve c. So again, we say line integral, even if what we're drawing is not a straight line. So here's a picture of the curve. Maybe actually, because, let's just draw the curve C in red. So the curve is actually, there's a point 3 comma 9 here. There's a point negative 3 comma 9 there. And the curve actually, it's kind of funny. It looks like this. So, whoops, I'm trying to draw a straight, completely horizontal line. And we'll travel like that. Okay. So what we have here, just for clarity, is this part is part of the parabola y is equal to x squared. So that's where the 3 comma 9 and negative 3 comma 9 come from. So here's the thing about this is that to answer the question here, we are going to need to split things up into 2 separate curves. So there's a curve C1. Let's say that that's the parabola part. Okay, the curve below. And for that, a parameterization could be x of t is equal to t, right? So for this part, just that part there, x of t equals t. Y of t is equal to t squared, right? So, I mean, if x is just t, then y would be t squared to get x squared. And then t would go between negative 3 and 3. Okay, so maybe it's a little unusual for us to have seen parameterizations where t goes from and to the number negative 3 and 3. We're so used to 0 to 1 for line segments. We're so used to 0 to 2 pi for a full circle, things like that. But just on a practical level, just using x and t to mean the same thing for this parameterization made it much simpler to parameterize a parabola. There are other options, certainly, but I think this is the easiest thing to do. But we also need to parameterize a second curve. That's this top part here. So there's the line segment. Okay, so let us parameterize the line segment from 3, 9 to negative 3, 9. So how about x of t equals, well, we start at 3, and then the change in x happens to be negative 6. Y of t is just constantly the value 9. And here, more familiarly, t would go from 0 to 1. The point is, the integral that we were asked about, the integral over c of the function f of x comma y, or we could just write y over x here already ds, this is actually going to be the integral over c1 union c2. So sorry for the union symbol if it's been a while since seeing interval notation in like an algebra class, but I'm just using sort of standard set notation found in like a how to do math proofs type class. Don't worry about it too much here though. It's just, we're just talking about we need that the stuff coming from that shape, we need the stuff coming from that shape as well. And all we really do here, to be honest, is we're just going to integrate over the first curve. So yeah, integral over c sub 1 of y over x ds, and add that to the integral over the second curve. integral over c sub 2 of the function y over x ds. That's all we're going to do. Okay, so if we set up the first integral, it's an integral, so t goes from -3 to 3 of y over x. Well, y is 9. Oh, sorry, I'm using the wrong one. We got to use this. So y is t squared, and then x is t. Yeah, and then ds for this first parameterization is going to be root. Okay, differentiate t, and you get 1. We should square that, even if that doesn't change the value. Let's write in that square. We need to differentiate y and have 2t, and then we should square that, dt. Let me copy this plus sign here. Maybe I'll just use an arrow to point. And then the second integral is just using the second parameterization. So we'll have an integral, t going from 0 to 1. We again have y over x, but the parameterized version. So 9 over 3 minus 6t. So 9 over 3 minus 6t. And then the ds gets replaced with the derivative of 3 minus 6t. Yeah, so -6, quantity squared. We need to differentiate 9 with respect to t. That'll give us 0. Again, let's just go ahead and put in the square. Just be kind of good about being consistent here. Okay, both of these integrals can be done. So we'll stop here. We'll just comment that, both integrals, if you want to go all the way through both integrals, I believe they just need u substitution. Need just a good old basic u substitution, and we won't go through the details right here, right now. Okay, so I'll just comment that this maybe seems strange because we took the line in quotes, the curve that was given, and we broke it into two separate pieces just because there was no way that one formula was going to do the whole thing. All right. If you want, instead of having two separate things and two separate integrals, I guess in well, you can't get away from two separate integrals, but if you wanted one parameterization, I guess you could do something piecewise, but, what's the point, right? So let's just say the following about this particular curve. Say you started at, let's see, where did we start, actually? Let's see. I guess we started here, okay? Just based on kind of how this is written with the -3. So say you start here, and you follow along the path of a curve, and then you end up right back where you started. So we travel around, and doop, there we are. We're back to right where we started. That is called, this is an example of what is called a closed shape. Let's write this a little better here. Okay, so the curve in red in the upper right, this is an example of a closed shape. We happened to travel counterclockwise, right? We traveled counterclockwise travel, and this kind of thing, closed shape, counterclockwise travel, this is quite typical. Is typical of a thing that goes by the name of a contour integral in another class. So don't worry about it here. You don't need to know this terminology for this class. I'm just pointing out that this is typical, kind of reminiscent, let's say. It's not exactly the same, but it's the idea behind a type of integral called a contour integral, which is found in a class that goes by two different names at different schools. Even the same school, sometimes the name of this type of class changes, so I just thought I'd just mention some connections. Sometimes the class is called complex analysis. Sometimes the class is called complex variables. Okay, but it's a class that does, in a nutshell, calculus, where your functions, inputs, and outputs are complex numbers. Anyway, don't worry about it too much. I just wanted to make the connection that integrating over a path that is closed, a closed loop as it's called, is very typical in that class. For us here, this was just an excuse to say, you know what, one parameterization alone didn't nicely describe the object that we're integrating over, so we just split it up into two separate parameterizations and just integrated over each piece separately, so we just created a sum.